Let us start this lecture with a thought process from Mahatma Gandhi. The best way to find yourself is to lose yourself in the service of others, and which is not being followed today by majority of people. So, let us recall what we learnt in the last lecture. Basically, we are trying to analyze the one dimensional spherical droplet under quiescent atmosphere, and we have derived the relationship considering or eliminating the source term, considering both the fuel and the temperature or the energy equation. And there we have already once integrated, and if you look at, we get this equation D can be rewritten as equation D can be rewritten as RS square B minus Bs plus 1 is equal to R square rho dV by dr. So, if I can separate the variables, and then we can integrate it by using separation of variables, we can have RS square by there should be alpha, right, rho alpha is dr by R square is equal to dB by B minus Bs plus 1, right. If you look at continuity equation, from continuity we can get mass flux of Rn square is nothing but your F/Rs square. That means whatever the mass is being generated at the surface of the droplet will be conserved across along with the radial direction. So, that way we can use that. Okay. Does that make sense? So, if we do that, then we can integrate the above equation . We can have alpha 1 by R is minus is equal to ln B Bs plus 1 plus C, and we will have to apply the boundary condition. That boundary condition we are having, R is tending towards infinity, B is equal to B infinity. That means, in this equation, right, if R is equal to infinity, what is happening? This is basically 0, this will be 0, right, and C will be what then? C will be then ln minus it will be B infinity minus Bs plus 1. Okay. So, then we can have that basically then we can have one by R is equal to ln B infinity Bs plus 1 divided by the, I can make it this bracket, Bs plus 1. In other words, you can write it down basically as F is equal to rho alpha, if I take that rho alpha by Rs square R ln Bs plus 1 B minus Bs plus 1. So, we will have to now apply a boundary condition again, right, at R is equal to Rs. What is that? That is basically B is equal to Bs, right. So, if you put that thing here, right, I can get simplified this one, right, m dot f, because I want to find out what is the mass flux at the surface, because this is a general term, right. This is a mass flux at different r, any r you can have, but you want to find out mass flux Fs, right, at the r, what it would be? It will be rho r by Rs ln by Bs plus 1, and this will be basically 1, because B become Bs minus Bs plus 1, this is 0. So, this is nothing but your alpha by Rs ln B infinity minus Bs plus 1, right, this much you are getting. So, keep in mind that this is, I can say, this is basically, I can write down that mass flux, right, F, I can write down that as a S surface is nothing but your alpha by Rs ln B plus 1, because this itself I can take B, right, and B is basically is the transfer number which can be estimated using various expressions, right. For example, if I say BFT, right, we have basically considered VFT, it can be extended for any other thing, that is nothing but your B infinity minus Bs, which is nothing but your Cp T infinity minus Ts plus delta Sc Yf infinity minus Yfs at the surface, right, divided by Qv plus delta Sc Yfs minus 1. And similar expression you can get for B fuel oxidizer and your oxidizer and temperature. So, you keep in mind that this thing is known, like delta Sc will be known to you, Yf infinity will be known, right. What will be Yf infinity? Will be 0, right, and Yfs at the surface you need to find it out, right, and how you will find out, that is a very important one, right. And of course, you should know the surface temperature, T infinity always will be known, and Qv is heat of vaporization you will have to evaluate. Already we have looked at the formula for Qv, and all these things if you know, then you can get the VFT, and if you know this rho and alpha and then Rs will be known to you, you can find out mass flux consumption, how much mass is being consumed or being vaporized during the combustion process, right. And let us see how we can really get this, how we will get this Ts and Yfs, that is the very important question one has to ask, right. And for that, of course, the simplest way of doing is that you can take, look, you can take the tea boiling, but you know, then and then do that. But there is also another way of doing it. What we can do, we can basically estimate that B, we need to know either this Ts, if I know Ts, I can find out Yfs, right, and if I know the partial pressure also, I can find it out that. And for these purposes, what we will be doing, we will be using this various this transfer number, and then all transfer number will be same, then we can simplify. Let me talk about this transfer number. As I told, this transfer number is given by B is equal this thing, right, already being discussed, and then B OXT will be given like this, and this is V FOX, right. And values of typical transfer number B for typical fuel is given, right. Something isooctane 6.41 and benzene and then heptane, all those data are given, and kerosene, gas oil, light fuel, all those are, you can see that octane is a little higher number, and then this is 1.7. Keep in mind that this is in the logarithm, so therefore changes in this transfer number won't really affect the mass burning very much, right. So we will be seeing that, but now question arises how we can basically estimate properties at the surface like YFS and TS, that is the thing we will be doing that. So for that, estimating this, what we will be considering, B the transfer number of F and oxidizer is equal to B oxidizer and T, right. And if we look at that, I can say that in the combustion case, right, we will be considering where it is combusting, but let me write down the equation over here, that is FOX is nothing but your YF infinity minus YFS plus Y oxygen at the surface minus Y oxygen F, right. Divided by the YFS minus 1 plus Fy oxygen S is equal to Cp oxygen and temperature we are talking about, T infinity minus Ts delta Sc Y oxygen infinity minus Y oxygen S into F HV. In place of QL, I am just writing the full term now, Ts minus T infinity plus delta Sc Y oxygen S F, right. So at the for combustion case, keep in mind that these transfer numbers are valid for vaporization and combustion, okay. For combustion case, what is that? That is basically Y oxygen at the surface of the droplet, what it would be? It will be 0, right, at the surface of the droplet. You know, if you take a droplet, right, and there is a flame here. So at the surface, what will be? This will be oxygen cannot be penetrate into the through the flame. So therefore this will be 0 at this surface, right. If I say this is Rs, so this will be 0. And if it is far away, let us say some infinity, what will be the fuel? F infinity will be 0. So if that is the case, I can say this is 0, right. Oxygen at the surface, it is 0, right. And similarly YFS, Y oxygen S will be 0, right, and Y oxygen at the surface, this will be 0, right. If you do that, what I will get, then we can have Y oxidizer F plus YFS divided by 1 minus YFS, right, from this side, left hand side. Then I will get Cp T infinity minus Ts plus delta Sc Y oxygen infinity F divided by, of course, I can write down, this is basically this will be oxygen at the surface, this will be 0, right. So, I will be getting delta H V plus Cl Ts minus T infinity. So, this is, let us say, equation I am saying I, right. And then if you look at, I need to find out this YFS, and YFS and Ts are unknown, 2 are unknown, right. YFS and Ts are unknown. So, what I will do, I will basically YF F can be related as, note that YFS and Ts are unknown, but YF can be related to partial pressure. Pressure Pf, partial pressure, right. So, YF we know is nothing but your rho F by rho is nothing but your Pf by P molecular weight of fuel divided by molecular weight of mixture, right. So, then still we have not solved. So, what we will have to do, we will have to basically use the relate this partial pressure with respect to what, temperature, right. And for that we will have to invoke the Clapeyron equation by invoking Clapeyron equation. We can have ln Pf dt is equal to delta Hv by R Ts square, right. So, you can get this thing very easily, that is ln Pf by Pf reference, right, some reference you will take, reference is equal to delta Hv by R into T reference minus Ts. So, this is 3. So, all these 3 equation can be solved because 3 are unknown, right, and therefore, you can get those things, right, very easily, because what are the unknowns here? Unknowns are Pf, right, partial pressure, and Ts, and then your basically YFS. So, by solving these all 3 equation can be obtained by using equation I, I2 and I3, right. And but generally for the simpler way to do is that, simpler way you take Ts is equal to Tb boiling, right, and then it will be very easier thing to do, right, kind of things. And keep in mind that this we will be doing basically this thing. And the another thing I would like to also draw your attention, that if let us say if I will take Voxt, right, is nothing but your Cp T infinity minus Ts plus delta Hc Y oxy for the surface, I can look at this term, right, delta SC into F is equal to delta HV plus CL Ts minus T infinity, right. So, if you look at this term in the numerator is too small compared to what? As compared to delta HV. So, you can neglect it, right. Similarly, this term, that enthalpy change is also too small as compared to heat release, because that will be, what is that, T infinity to Ts will be very very small, because heat release will be much higher. So, this is also too small as compared to this term, right. See, always comparison, okay. And then I can say this is basically delta SC Y F into delta HV, which is very easier to find out because all are known. See, you are eliminating lot of things. Y oxidizer you will be knowing, F you know, delta SC know, delta HV know. Are you getting? This is of course approximation you will be. So, now we will stop over here and we will be discussing about how we can use this relationship for finding out basically burning rate and droplet diameter. How does the diameter of the droplet is changing with respect to time? And once we know how to find out that, then we can find out what is the droplet lifetime. That means how much time it will take to completely consume during the combustion. So, that we can look at in the next lecture.